In this segment of the Module 3 lecture, we're going to talk about the uses of the standard deviation. Often you hear, for example, on TV, every time they advertise about batteries, they may say, well, our batteries now last 30% more than, I don't know if other batteries or their own batteries or their competitors' batteries, who knows. But if you wanted to determine that, then, like for example, what proportion of batteries actually last more than 30%, then you will need to know the mean and the standard deviation of the data and frequency distribution to see their shape. So to determine that proportion, we need the standard deviation. So, depending on the shape of the frequency distribution, we will use either the empirical rule or this Chebyshev's theorem. So if the frequency distribution is symmetric and bell-shaped, like shown by this blue line, then we will use the empirical rule to determine the proportion of data within certain number of standard deviations about the mean. If the distribution is not symmetric, and of course it will not be bell-shaped, then we will be using the Chebyshev's theorem to find the proportion of data within a given number of standard deviations about the mean. So let's talk about the Chebyshev's theorem first. So Chebyshev's theorem specifies that at least 1 minus 1 over k squared of the values in the population lie within k standard deviations of the mean, where k has to be bigger than 1. If it is 1, then you can see that this quantity becomes 0. So, for example, the percentage of values in the frequency distribution within 2 standard deviations of the mean, or in other words, k is equal to 2, is 1 minus 1/2 minus 1 divided by 2 squared, which is this expression with k equals to 2. If you carry that operation and multiply by 100, you get 75%, meaning that there is 75% approximately of the data between the mean and 2 standard deviations below the mean and 2 standard deviations above the mean. Now, if the standard deviation is 3, then the proportion of observations between 3 standard deviations below the mean and 3 standard deviations above the mean is going to be 1 minus 1 over 3 squared, which is this. If you carry that operation and multiply by 100, then you're going to find that 88.9% of the observations will be in this interval, from the mean minus 3 standard deviations all the way to the mean plus 3 standard deviations. All right, let's look at an example. In this case, an arborist wishes to evaluate the recovery of trees in a particular region after a forest fire by determining the percentage of trees that have heights between 3 and 25 feet. So the heights of 142 trees were measured. From those 142 measurements, it was found that the mean is 14 and the standard deviation is 7.33. That dot plot of the heights is shown below, right here. And you can see that this clearly is not a symmetric distribution and obviously not a bell-shaped frequency distribution. So that tells us that the tool to use in this case is the Chebyshev's theorem. So, and that's I created a procedure to solve this problem. So the very first thing is by inspecting the dot plot of the observations, then we see that this thing is positively skewed. It's not symmetric, so the Chebyshev's theorem needs to be used in this example. The next step, we need to determine the number of standard deviations in that are spanned by this range from the mean to the lower value, from the mean to the upper value. So we need to know how many standard deviations are below the mean from 14 to 3, and how many standard deviations from 14 to 25. So we do that subtraction, and you see there are 11 values from 3 to 14, and 11 feet from 14 to 25. So we have the span is the same. And that's what we need, because in here we're looking at the given number of standard deviations above and below the mean. So the distance from the mean to whatever number of standard deviations below the mean to whatever number of standard deviations above the mean, it has to be the same. All right, so in this case, we find that the span is the same, 11 units below the mean and 11 units above the mean. To find how many standard deviations are spanned by these intervals, then we calculate k, which is 11, divided by 7.33, which is about 1.5 standard deviations. So with this number, now that we know k, we can apply the Chebyshev's theorem equation, and that's what we have here. So we have 1 minus 1 divided by 1.5 squared. If you compute that and multiply by 100, that's about 55.6%. Therefore, the arborist finds that about 55.6% of the trees have grown to be between 3 and 25 feet tall. And then from this determination, he can determine if the growth of this forest is healthy, and he can even perhaps predict how long it will be before the forest is back to how it was before the fire. So this is an example where the Chebyshev's theorem is applied to answer the question that this arborist is asking himself. All right, so now the other option is to use the empirical rule. So again, if the frequency distribution is symmetric and bell-shaped, then the empirical rule states that about 68% of the values fall within plus or minus 1 standard deviation of the mean. And 95% of the data values fall within plus or minus 2 standard deviations above the mean. And 99.7% of the data values fall within plus or minus 3 standard deviations of the mean. So graphically, we're showing it here. So the range between 1 standard deviation below the mean and 1 standard deviation above the mean, we have 68%. The range from 2 standard deviations below the mean to 2 standard deviations above the mean, we have 95%. And the range from 3 standard deviations below the mean to 3 standard deviations above the mean, we're going to have 99.7% of the data. Now, because this is a symmetric distribution, we can break these percentages even further. So, for example, in the range from 1 standard deviation above and below the mean is 68%. This is symmetric, so you can have 34% between the mean and 1 standard deviation below it, and 34% between the mean and 1 standard deviation above it. Now, if you look at the difference between 95% and 68%, and you divide it by 2, that's 13.5%. So you can, from this quantity, you can determine that the percentage of data that falls between 1 standard deviation below the mean and 2 standard deviations below the mean is 13.5%. Similarly, you can find that the percentage of observations 1 standard deviation above the mean, between 1 standard deviation above the mean and 2 standard deviations above the mean is 13.5%. Also, if you, using this calculation, you have 99.7% of the data minus 95%, 95% of the data, and then you divide that difference by 2, then you have 2.35%. So that tells you that 2.35% of the data is going to be between 2 standard deviations below the mean and 3 standard deviations below the mean. And 2.35% of the data is going to be between 2 standard deviations above the mean and 3 standard deviations above the mean. So this breakdown can help you to find even more fine detail of the proportion of data within ranges of standard deviations. All right, here's an example. This came from the fact that when I work in the manufacturing of semiconductors, we use microscopes a lot. And we all, the interpupillary distance of our eyes varies. So the microscope needs to have a range of the objectives so that they can accommodate to both of your eyes. So in this case, the interpupillary distance of 3,750 patients is displayed in this histogram. And you can see that this histogram is about more or less symmetric, and it seems to have this bell shape. Also from this data, we find that the average distance is 7 centimeters, and the standard deviation is 0.25 centimeters. Here's a figure showing you how the interpupillary distance is measured. Now, they're asking us here to find the approximate percentage of patients with interpupillary distances between 6.5 and 7.5 centimeters. All right, to do that, well, number one, what is the shape of the histogram? Well, we can see that it's symmetric and more bell-shaped. So in this case, we're going to apply the empirical rule. The next step is we need to find out how many standard deviations there are between 6.5, the lower value, or the lower limit that we're interested in, and the mean and the upper limit of the interval that we're interested in. So here we find that 7 minus 6.5 divided by the standard deviation, which is 0.25, and 7 is the mean, of course, that the distance is equivalent to 2 standard deviations. And the distance between 7.5 and the mean, 7, and we divide that by the 0.25, then we see that that distance is 2 standard deviations. So the range from 6.5 to 7.5 is 2 standard deviations below the mean and 2 standard deviations above the mean. So using the empirical rule, we know then that 95% of individuals have interpupillary distances between 6.5 and 7.5 centimeters. So that's how we can apply the empirical rule to find the proportion of individuals, in this case, that have the interpupillary distance between 6.5 and 7.5 centimeters. I found this cartoon, I found it very interesting, because if you look at, for example, your income, well, your income is very low with respect to the incomes of every other person in the population, and that tells you that, well, you're in a pretty poor situation. And maybe a lot of people with the pandemic find themselves in such a bad situation. Again, the empirical rule is used to say this. All right. And again, just remember that the Chebyshev's theorem is used for distributions that are not symmetric and not bell-shaped, and the empirical rule is for distributions that are symmetric and bell-shaped. And that we are always calculating the proportion of values between the mean and a given number of standard deviations. Okay, in the next recording, we'll talk about the measures of position.